Dynamic line rating (DLR) is far from just a buzzword in the energy sector. It's a game-changing technology that can significantly enhance power transmission efficiency, reliability, and sustainability. With rising demands on our energy grids and a pressing shift toward renewable energy sources, grasping the concept of DLR is essential. As the world moves towards smarter, greener grids, understanding DLR becomes not just important, it's vital. Dynamic line rating is an innovative technology that optimizes the electrical carrying capacity of overhead power lines. Unlike traditional static ratings, which are based on conservative worst-case environmental scenarios, DLR uses real-time data to provide a dynamic and accurate assessment. This enables power lines to operate closer to their true capacity without compromising safety, leading to more efficient utilization of transmission infrastructure. The effectiveness of DLR is driven by advanced sensors and algorithms. Sensors installed on or near the power lines continuously monitor variables such as ambient temperature, wind speed, and line sag. This data is processed in real time, allowing grid operators to dynamically adjust the line's capacity. Consequently, DLR not only boosts grid efficiency but also supports the integration of variable renewable energy sources like wind and solar into the system. Overhead transmission lines are utilized for the transmission of electrical power. The current that is transported causes the conductors to heat up, while the ambient temperature and especially the wind cool the conductor. Traditionally, overhead lines are designed using conservative ambient conditions. The combination of values for ambient temperature, effective wind speed, and solar radiation are rarely exceeded. This means that most of the time, the current carrying capacity is higher than the design rating. This potential can be unlocked using dynamic line rating. Here's how dynamic line rating works to prevent overheating of power lines. Real-time monitoring. DLR systems involve the use of sensors and weather stations to monitor real-time conditions such as ambient temperature, wind speed, solar radiation, humidity, and conductor temperature. Weather and environmental data integration. The collected data is then integrated into computational algorithms that consider the various factors affecting the conductor's temperature and heat dissipation, such as wind cooling and solar radiation. Thermal modeling. Advanced thermal models are used to predict how the power lines will respond to the current flowing through them under the given weather conditions. These models take into account the line's material properties, dimensions, and the surrounding environmental conditions. Dynamic rating calculation. Based on the real-time data and thermal models, the DLR system calculates a dynamic line rating, which is the maximum permissible current that the line can carry at that moment without exceeding its safe operating temperature. Operator interface. Grid operators have access to the dynamic line ratings through control systems and software interfaces. These interfaces provide information on the current line capacity and allow operators to make informed decisions about how much power can be safely transmitted through a particular line. Load management. With the dynamic line ratings, grid operators can manage power flows more efficiently. During times of high demand or congestion, they can optimize the use of transmission lines without compromising safety. Alerts and alarms. DLR systems can also provide alerts and alarms when line ratings are getting close to their limits, enabling operators to take preventive actions such as rerouting power, shedding load, or implementing emergency measures. Improved grid reliability and efficiency. By allowing power lines to operate closer to their actual capacity under safe conditions, DLR systems help improve the overall reliability and efficiency of the power grid. This can also support the integration of renewable energy sources by maximizing the use of available transmission capacity. It's important to note that implementing DLR requires a combination of accurate weather forecasting, advanced sensor technology, computational modeling, and effective communication between grid operators and DLR systems. Additionally, regulatory and safety standards play a crucial role in ensuring that DLR implementations meet the necessary safety and performance criteria. Question is: how does dynamic line rating work? DLR utilizes an array of sensors to continuously monitor various conditions such as weather, line sag, and temperature. These sensors, strategically positioned along transmission and distribution lines, gather data on variables like conductor temperature, line angle, ambient temperature, and wind speed. Advanced software algorithms then analyze this data to determine the line's current capacity in real time. This monitoring allows utilities to maximize the use of existing infrastructure and delay expensive upgrades. Dynamic line rating and renewable energy integration. The integration of renewable energy sources like wind and solar presents unique challenges for power transmission due to their variability and often remote locations. DLR excels in this scenario by enabling utilities to dynamically adjust line ratings. This ensures that the grid can accommodate fluctuations in energy production, facilitating the seamless integration of renewable sources. Challenges and solutions of dynamic line rating. DLR technology faces several challenges. Accurate weather data is essential for its effective operation, and coordination among stakeholders such as utility companies, regulators, and grid operators is critical. Question is: why is DLR important and why should you use it? Implementing dynamic line rating provides numerous benefits crucial for modernizing the energy sector. DLR delivers a range of advantages: enhanced safety, operational efficiency, sustainability, and cost savings that make it vital for a modern, resilient power grid. By leveraging real-time data, DLR enables rapid decision-making to prevent line overloads and faults. Furthermore, it increases the capacity of existing power lines, reducing the need for new, costly infrastructure. With the capability to adapt dynamically to environmental conditions, dynamic line rating also facilitates the seamless integration of renewable energy sources, thereby contributing to global sustainability objectives. These advantages collectively result in considerable cost savings, making DLR an indispensable tool for a resilient, efficient, and future-ready power grid. Safety enables real-time, proactive decisions to mitigate risks. Efficiency maximizes the utilization of existing lines, eliminating the need for new infrastructure. Sustainability eases the integration of renewables, supporting carbon reduction efforts. Cost savings brings economic benefits through effective line management. These benefits position DLR as a fundamental component for any power grid focused on long-term sustainability and efficiency. Harnessing the power of dynamic line rating. Traditionally, power lines have been operated under conservative ratings to ensure safety and reliability. These static values, however, often fail to consider real-time factors such as load, conductor temperature, and weather conditions. Dynamic line rating transforms this approach by continuously monitoring and analyzing these variables, determining the maximum permissible current a power line can safely carry at any given moment. A DLR system, driven by advanced algorithms and real-time data, enables grid operators to increase power transfer capacity, safely transmit more electricity through existing lines, minimizing the need for costly infrastructure upgrades. Enhanced grid reliability. Precise measurement of line capacity reduces the risk of overloading and power outages. Facilitate renewable energy integration. Dynamically adjust line ratings to accommodate the fluctuating output of renewable energy sources. Optimize grid operations, reduce congestion costs while improving overall grid efficiency. Revolutionizing electric transmission. Dynamic line rating is a cutting-edge solution designed to enhance the capacity of global electric grids by monitoring real-time line conditions. This innovative approach not only increases conductor capacity but also reduces congestion costs and facilitates the seamless integration of renewable energy sources. Key benefits of dynamic line ratings. Enhanced transmission capacity. By increasing the current carrying capability of transmission lines, DLR effectively reduces congestion costs, allowing for more efficient energy distribution. Renewable energy integration supports the effortless integration of renewable energy by dynamically adjusting line ratings to accommodate variable outputs. Real-time reliability. By delivering dynamic line ratings in real time, DLR ensures that grid operators maintain compliance and reliability under varying conditions. DLR leverages advanced technology to maximize transmission line capacity. Real-time data acquisition continuously gathers critical information on weather, conductor temperature, and other essential factors to provide an accurate assessment of line conditions. Advanced modeling employs sophisticated models combined with real-time data to predict line capacity with precision. Dynamic rating calculation frequently updates line ratings to reflect changing conditions, ensuring optimal performance. Seamless integration. DLR integrates smoothly with existing grid management systems, enhancing overall grid operations without disruption. Take an example, benefits of Ampassement's DLR solution. By adopting Ampassement's Grid Boost, grid operators can tap into significant benefits, such as up to 40% increase in transmission capacity, drastically enhance the power transfer capabilities of existing transmission lines, optimizing grid performance. Reduced congestion costs, improve grid efficiency by reducing congestion, resulting in more cost-effective operations. Compliance with FERC Order No. 881 guarantee adherence to regulatory requirements, ensuring operational integrity and reliability. Let's discuss the challenges of traditional sensor installation. Conventional methods for installing sensors on power lines are often labor-intensive, risky, and costly. These installations generally require a significant amount of equipment, specialized personnel, and can result in extended power outages, all of which hinder the widespread adoption of DLR technology. Ampassement's drone-powered solution. Ampassement has developed an advanced, drone-based system that simplifies the installation of DLR sensors on power lines. This innovative approach removes the need for human intervention in hazardous conditions, significantly reducing both installation time and costs. Ampassement's drones are equipped with state-of-the-art sensors and robotic arms, allowing for the precise attachment of DLR sensors to power lines with minimal disruption. These drones can operate autonomously or under remote supervision, ensuring safe and reliable installations. Benefits of drone-powered installation. Increased safety, minimizes the risk of accidents and injuries associated with traditional installation methods. Cost reduction, eliminates the need for costly equipment, specialized personnel, and power outages. Improved efficiency, facilitates the rapid installation of sensors across large areas, enhancing operational speed. Enhanced grid reliability, provides real-time monitoring capabilities, enabling early detection of potential issues. Accelerated DLR adoption, makes DLR technology more accessible and affordable for grid operators. Unleashing the hidden strength of our power grids are robust, yet they often underestimate their own capabilities. While transmission lines have a rated capacity, real-time weather conditions can actually allow them to carry more power. This article delves into dynamic line rating systems, innovative solutions that adjust transmission line capacity based on real-time weather data, thereby unlocking the full potential of our grids. Challenges and solutions for dynamic line rating system. Conservative capacity limits. Traditional line ratings are set conservatively to account for worst-case scenarios, which can lead to underutilized transmission lines and wasted capacity. Dynamic line rating systems utilize real-time weather data such as temperature, wind speed, and solar radiation to calculate the actual capacity a line can safely handle. Imagine a transmission line operating at 70% capacity when it could actually handle 100% on a cool, breezy day. Integration with grid operations. Real-time data from dynamic line rating systems needs to be seamlessly integrated with grid control systems. This allows for dynamic adjustments to power flow and increased utilization of transmission capacity. Picture the grid receiving real-time updates on line capacity and optimizing power flow accordingly. Data accuracy and reliability. Accurate and reliable real-time weather data is crucial for dynamic line rating systems. Research focuses on advanced sensor technologies and communication protocols to ensure data integrity and security. Imagine a network of sensors continuously monitoring weather conditions around transmission lines. Research focus, optimizing line capacity with real-time data, developing advanced sensor technology. Research explores cost-effective and reliable sensors that can measure weather conditions relevant to line capacity, such as ambient temperature, wind speed, and conductor sag. Picture tiny sensors attached to transmission lines collecting real-time data, data analytics, and predictive models. Research focuses on advanced data analytics and machine learning algorithms to process real-time weather data and predict line capacity with high accuracy. Envision AI systems analyzing sensor data and providing real-time line capacity recommendations. Cybersecurity considerations. Ensuring the security and reliability of data communication is paramount. Research focuses on developing robust cybersecurity measures to protect dynamic line rating systems from cyber attacks. Imagine a secure and encrypted data network for real-time weather information. Research questions and answers. What are the potential benefits of dynamic line rating systems? Answer: Yes, they can increase transmission capacity, reduce energy waste, and facilitate the integration of renewable energy sources. How soon can we expect to see widespread adoption of dynamic line rating systems? Answer is significant advancements are being made, with pilot projects already underway and widespread adoption expected within the next decade. Dynamic line rating is a technique used in the power industry to prevent overheating of power lines by adjusting the permissible current carrying capacity of the lines based on real-time weather conditions and other relevant factors. Traditional static line ratings often assume worst-case scenarios, leading to underutilization of the power grid's capacity. DLR, on the other hand, allows power grid operators to optimize the use of transmission lines while maintaining safety and reliability. Dynamic line ratings are an integral part of preventing liability and assuring safety. How to apply dynamic line rating? It is a common misconception that sensors are necessary for DLR. This is not true. DLR calculations can be performed solely based on weather data. When a forecast is needed, e.g. 2-day or 10-day forecasting, weather data serves as the primary input. However, weather forecasts can be highly unpredictable, particularly for wind speed and direction. Therefore, many suppliers offer sensors. Sensors measure in real time, allowing any system that uses sensor data to provide a near real-time prognosis. The best approach is likely a combination of both weather data for the prognosis and sensors for real-time validation. The data can also be evaluated afterward. Some suppliers offer improved weather data based on machine learning methods that use historical weather data and sensor-measured data as input. How does a DLR sensor work? There are various methods to monitor the condition of a conductor, but it ultimately comes down to determining the sag of the conductor between two towers. You can explore different measurement options in this article. Most sensors measure temperature and vibration, while some also measure movement and tilt. One of the crucial aspects is to measure the entire span of the conductor. A spot measurement local conductor temperature often does not provide a comprehensive understanding of the conductor's condition. DLR sensors play a crucial role in assessing the real-time condition of overhead transmission lines. Here's a brief explanation of how they work. DLR sensors monitor the state of a conductor, primarily by determining its sag between two towers. This helps in understanding the line's current carrying capacity. These sensors typically measure temperature, tracks how hot the conductor is. Vibration assesses the conductor's movement. Movement and tilt. Some advanced sensors also measure these factors to provide a more comprehensive view. Span coverage. It's essential to measure the entire span of the conductor rather than just a single spot. This ensures a more accurate assessment of the conductor's overall condition. By utilizing both weather data and real-time sensor data, DLR systems can optimize the transmission line's performance, ensuring reliability and efficiency. Functionality of DLR sensors are instrumental in monitoring and optimizing the performance of overhead transmission lines. They assess the real-time condition of the conductors, primarily by measuring the sag, which is the downward bend of the conductor between two towers. Key measurements. Temperature. One of the critical factors affecting the conductor's performance is temperature. DLR sensors track the conductor's temperature to prevent overheating, which can lead to sagging and, potentially, electrical failures. Vibration. These sensors measure the vibration of the conductor caused by wind and other environmental factors. High vibration levels can indicate potential issues with the conductor's stability and integrity. Movement and tilt. Some advanced sensors also measure the conductor's movement and tilt to provide a comprehensive understanding of its physical state. Importance of measuring the entire span. A crucial aspect of DLR sensors is their ability to measure the entire span of the conductor rather than just a localized spot. Localized measurements might not provide an accurate picture of the overall condition of the conductor. By monitoring the entire span, DLR sensors ensure a more precise and comprehensive assessment. Integration with weather data. DLR systems can be integrated with weather data to enhance their accuracy. This integration allows for better forecasting and real-time adjustments based on changing environmental conditions such as wind speed, direction, and ambient temperature. By combining weather data with real-time sensor data, DLR systems can optimize the transmission line's performance, ensuring reliability and efficiency. Benefits of using DLR sensors. Increased efficiency. By accurately monitoring and optimizing the conductor's condition, DLR sensors can increase the current carrying capacity of transmission lines. Improved reliability. Real-time data allows for prompt actions to be taken in case of potential issues, reducing the risk of electrical failures. Enhanced forecasting. The integration with weather data provides better forecasting capabilities, ensuring that the transmission lines operate within safe limits under varying environmental conditions. In summary, DLR sensors are essential tools for ensuring the efficient and reliable operation of overhead transmission lines by providing real-time monitoring and optimization based on accurate and comprehensive data. Advanced details on DLR sensors, principles of operation, sag monitoring. The primary goal of DLR sensors is to monitor the sag of the conductor, which is the downward bend that occurs due to various factors such as temperature, load, and environmental conditions. Excessive sag can lead to unsafe clearances from the ground or other objects. Types of DLR sensors. Thermal sensors. These sensors measure the conductor's temperature, which directly impacts its sag and tension. High temperatures cause the conductor to expand and sag more. Strain gauges, used to measure the mechanical strain on the conductor, indicating changes in tension and sag. Vibration sensors. These sensors detect the vibration frequencies of the conductor, which can be influenced by wind and mechanical load. Analyzing vibration patterns helps in understanding the mechanical behavior of the line. Laser-based distance measurement. Advanced DLR systems may use laser-based devices to measure the distance between the conductor and the ground, providing precise data on sag and clearance. Types of DLR sensors. Thermal sensors. These sensors measure the conductor's temperature, which directly impacts its sag and tension. High temperatures cause the conductor to expand and sag more. Strain gauges, used to measure the mechanical strain on the conductor, indicating changes in tension and sag. Vibration sensors. These sensors detect the vibration frequencies of the conductor, which can be influenced by wind and mechanical load. Analyzing vibration patterns helps in understanding the mechanical behavior of the line. Laser-based distance measurement. Advanced DLR systems may use laser-based devices to measure the distance between the conductor and the ground, providing precise data on sag and clearance. Data integration and analysis. Weather data integration. DLR systems often integrate weather data, such as wind speed, direction, ambient temperature, and solar radiation, to provide a comprehensive analysis of the line's condition. This data helps in predicting the thermal behavior and sag of the conductor. Real-time analysis. By continuously collecting and analyzing data in real time, DLR systems can provide immediate feedback on the conductor's condition. This allows for dynamic adjustment of the transmission line's operating parameters to ensure safety and efficiency. Historical data and machine learning. Some DLR systems use historical weather and sensor data, combined with machine learning algorithms, to predict future conditions and optimize line performance. This approach improves the accuracy of forecasts and helps in preventive maintenance. Benefits of DLR systems. Enhanced capacity. By accurately monitoring real-time conditions, DLR systems can safely increase the current carrying capacity of transmission lines, maximizing the use of existing infrastructure. Improved reliability. Continuous monitoring and real-time data analysis help in identifying potential issues before they become critical, reducing the risk of outages and ensuring a more reliable power supply. Cost savings. By optimizing the performance of existing transmission lines, DLR systems can delay or eliminate the need for costly upgrades or new installations. Challenges and considerations. Weather variability. Accurate weather forecasts are crucial for effective DLR implementation. However, weather conditions, especially wind, can be highly unpredictable, posing a challenge for precise monitoring and forecasting. Data accuracy. Ensuring the accuracy and reliability of sensor data is essential. Any errors or inconsistencies in the data can lead to incorrect assessments and suboptimal performance. Integration with existing systems. DLR systems need to be seamlessly integrated with existing grid management and control systems to provide real-time insights and enable dynamic adjustments. In essence, DLR sensors and systems represent a sophisticated blend of mechanical, thermal, and environmental monitoring technologies that work together to optimize the performance and safety of overhead transmission lines.